So I'm going to move on to 5.1, which is all about E. And the annoying thing about E is they don't really show proof that f of x is equal to ex and that the derivative of that is also e to the x. They pretty much just say, pull open a standard graph and use your standard limit for h, and then you'll see that when a is 1, the rate of change is the same as the y value. See, there's the y value, and here it is for x is 2. And you'll see the rate of change 7.8 is the same as the y value. So they just say it intuitively. And what's also really annoying is if they put e to a different exponent, let's say they put it to 3x squared plus 2x, they also don't explain, they just say, well, you do the chain rule. So the derivative of that is going to be equal to exactly that times the derivative of the exponent. So the derivative of that up top is 6x plus 2. And you can either leave it like this or distribute it through, but they also don't explain that. So they just tell you, examine it in a graph a few times and you'll see, and it just doesn't sit well, as far as I'm concerned, at proving it. And so you can see here the rate of change when a is 2 is something like that. And then when you go down and actually calculate it, you get the same result, slightly off, but same idea. And you don't really end up proving it. So I put a rudimentary proof up. I'm just going to leave it like that. And then they just summarize the end of the chapter. And they also want you to revisit the properties of growth curve and make sure you understand a growth curve. And they just essentially say, here's the derivative. And then they ask you to do it again for different exponents. As I just said, the derivative of e to the 3x is the same as 3 times the original function. And they just set the rule. The derivative of e with a different exponent is just e to that exponent times the derivative of the exponent using the chain rule. And they go through a few strategies and explain what you should do and how much you should simplify it. Sometimes they leave it unsimplified like this. And then sometimes they simplify it like that. And they ask for specific cases. But I'd say it's a lousy chapter for explaining the process. And then they just summarize it. Use the chain rule. The slope of the tangent of the point of ex is equal to the value of that point. The rules still apply, etc. And that Euler's number is just a number. Okay. Let's see if we can answer some questions. And again, I'm probably not going to do the theoretical. I'm not a big fan of E. I mean, it's an interesting number. It doesn't have a lot of practical purposes. And be aware that log based E to the whatever is the same as ln of 2. Log base E, that's what ln is. It's a log with a base E. And just as log unwritten without a base means base 10, ln unwritten will never have anything written because it's always base E. It's essentially a ln is equal to a log with base E. So be aware of that. If ever you need to do it in your calculator, for instance, suppose your calculator doesn't have ln, and you need to do the ln of 5, you would do log of 5, and you would divide it by the log of E. And that will spit out the same thing. Go ahead and do your calculations if you want. Same with logs of different values. So if you wanted to find the log of base 2 for 7, you would take the log of 7 and divide it by log of 2. Or you could also take the ln of 7 and divide it by the ln of 2. All these properties are useful when you actually derive things. What can you not use the power rule for derivatives to differentiate this? Because the exponent e is just a number, and the exponent is the actual x. So you can't really follow that technique. It makes no sense. So let's see if I can get rid of all that junk. No, I can't. Weird. Anyway, let's see if I just click this forever. There we go. I'm just going to do that. 2. Differentiate each of the following. Fair enough. I'm going to start with that one. Now notice it has an exponent, which means the derivative is the exact same thing times the derivative of that. What's the derivative of that? So when I want to do derivative of something, I'll just do this. And it's 3. So that means we simply, we simply put the derivative of this, which I'm just going to write as that, is 3e to the 3x. Pretty straightforward. They just want you to get used to it. What's the derivative of this? Notice it doesn't matter if it says s is equal or y is equal or x is equal. The derivative of this is the same thing times the derivative of the exponent. Numbers don't have derivatives, so the derivative of this is just 3. And again, I just put 3 in front of that. And if I want to calculate the derivative of s, I now have s prime is equal to this. If they give me values of t, I can figure it out. And you'll also never find a max or min on a growth curve. It has no max or mins. What's the derivative of this? Same rules. The derivative of this is the same function times the derivative of 10t, which is 10. The 10 can multiply the 2. So 2 times 10 is 20. So the derivative of this, y prime, is equal to 20 times e to the power of 10t. What's the derivative of this? It's the same rules. It's the derivative of this is equal to that times the derivative of this up here. The derivative of that up there is 3. So if you can want to think of it as this, u to the, I don't know, s, you're taking the derivative will always be u to the s times the derivative of s. Now, let's just keep going. Here's e. Again, we're going to focus just on this. The derivative is whatever the e exponent is. And what's the derivative of this? It's just minus 6 plus 2x. Now, what's interesting about this is you can leave the derivative of this as a multiplier out front if you want. Or you can simplify. You can distribute it. Now, there's really no need to distribute it, especially since it's easier to plug in values of x here and solve this bracket than it is to create twice the work. If your teacher wants it simplified, they'll say it. And then finally, something like this is somewhat interesting, but not really. The derivative of this is this times the derivative of this, and you would use the chain rule if you had to, if there was something unique in there for 2x. The chain rule says I bring the half down in front, and this goes to minus a half, which is essentially 1 over 2 times square root of x, which means the derivative of this is actually just that divided by that. And it's 2 times. It's not an exponent or anything. If this x was even more complicated, you'd have to take not only the chain rule for the square root of x, but you then have to multiply by whatever's in there. So if, let's say, if it was x squared, you'd have to do another 2x here. So you can see it can get quite complicated, especially if you have like a quotient as a exponent. All right, let's move on to this part. Okay, what's the derivative of this? I see what they're doing. It's exactly what I just said. So the derivative of this is the same thing times the derivative of x cubed, which is 3x squared. 3x squared times the 2, it becomes 6x squared is the derivative. So I have to multiply this out, and then if I'm going to find x, I have to solve this separately. As an example, if I was looking for x is equal to 1 or 2, let's use 2. I put the 2 in here, I get x squared, 2 squared is 4, times 6, I get 24. I take e, 2 cubed is 8, so I have to multiply 24 times e to the power of 8. I'm not going to resolve that, but that's essentially 2.71 to the power of 8 times 24. Okay. What about stuff like this? Well, you have to use the quotient rule. The quotient rule says I'm going to take the derivative of that, which is just 1. No, I'm just going to take that times the derivative of this. Well, this is where it's easier to assign things. I'm going to let f of x, I'm going to make it a little bit bigger. I'm going to make f of x equal to the numerator, which means I want to find f prime of x. And I'm going to make g of x equal to the denominator, and g prime of x is equal to 1. So they made it a little easier on me. Since this is the numerator, what's the derivative of it? Well, it's the same thing times what's up top, the derivative of top, minus 3x squared times minus 3x squared, which means the derivative of f of x is equal to minus 3x squared times e to the power of this. Now, I like to put the multiplier out front because sometimes when you punch it into like Desmos, it gets confused about what's happening after e, which means the quotient rule is simply g of x times f prime minus f of x times g prime. Fortunately, g prime is just 1, and all of it over g of x squared. Well, g of x squared here is just x, so g of x squared is x squared. Then you just replace bit by bit in here, so I have a g of x I know is x, and I'm multiplying it by f prime, which I now know is this. I'm going to replace the word f prime with this. And I'm going to subtract f prime, or f of x, which I know is this. Now, sometimes you can find solutions. For instance, expand a bit. X squared times this is 3x squared, 3x cubed now. So I can get rid of the x. And sometimes you can simplify it. Notice they both have e to the x minus to the x. They all have this in them, which makes sense because so many of them have the same thing as the function. So if I factor out that, I'm left with this. And I don't believe I can simplify it any further. There's no cancellation here because you can only cancel out things when the same base. Well, that's not the same base up there. So you're left with this. So e to the minus x cubed times this bracket, which is minus 3x squared minus 1, all divided by x squared. Just to see if we got it right, this is 3b. So we're going to just grab 3b and see if we got it right. Well, it's actually 3c. Okay, I'm going to grab it all because it's hard to grab it individually. And there it is, right there. They left it, and it looks like they didn't quite do it properly, because there's supposed to be an x here. It looks like this should have become cubed, because f of g of x is that, and it gets multiplied times f prime. Interesting. I think they got the cube wrong, but otherwise we got the same thing. They just didn't factor out the e to the minus x to 3. I'll continue checking to make sure we're on the right course. But you can see how complicated it gets. This, I just have a square root as an x as a multiplier. However, that's the same as x to the half times e to the x, and I have to treat this as the product rule, which says I'm going to take this times the derivative of that, which is pretty much the same thing, and I'm going to add it to this times the derivative of that, which ends up being 1 over 2 times square root of x. If you can't get it at this point, it's pretty much that. It's pretty much the same thing. And there's no really solving it more after that. I guess you could put them over the same fraction. Let's see if they bothered with the same fraction. They did not. So you can see that's it there. They even left it the same way I did instead of putting e to the x on top. But it's exactly as written. Okay, what about this one? This one, that's interesting here. I don't know if they meant to write that. I think this is just e as a multiplier. So it's treated as a number. So this whole thing I can just take the derivative of, and I get 2et plus the derivative of this is the same thing times the derivative of minus t, which is minus 1. So the only thing that happens is this changes to a negative. So you get 2 times e times t minus 3 times e to the power of minus et. Interesting and weird. Let's see if we got any of that right. So 2t, oh, it looks like it was supposed to be to the t squared. So maybe I just copied it down from the textbook wrong. Let's see. Yeah, somehow it didn't copy properly from the textbook. No, I got it right. So they're saying, yeah, I don't know why they have et to the squared, because et to the squared was never that. It was never, I think they've misprinted that. I think that was supposed to be et to the squared instead of e multiplier times t to the square. Because it's clear here that and it also made no sense when I saw it. That's just a misprint. That's supposed to be e to the t powered square. We're going to skip it. You get the idea of that one anyway. It wasn't rocket science. Here you had to take the quotient rule. So again, the quotient rule says I'm going to take the bottom quotient and multiply it by the derivative of the top of the numerator, and I'm going to subtract the top quotient multiplied by the derivative of the bottom, all of it with the bottom squared. Well, g of x is the bottom, so I'm going to just take it like that. The prime of this one, which is f prime here, is 2 times that. So that's the prime. Minus the numerator times the prime of the bottom. The prime of the bottom is, again, 2 to the e to the 2t. So I'm getting, interestingly enough, minus 2 here And if you look at these things, this e to the 2t and this e to the 2t are multiplying each other. And it's two bases that are the same. So you're left with minus 2e to the 4t, because you can add the exponents of things that are the same base. Which means I've got this whole thing here, just move it over, is equal to this, minus 2 to the e to the 4t. I could expand, yeah, I mean, okay, this might be interesting. I'm going to expand this top. So I get 2 times e to the 2t, where the 1 is. But here, I'm going to get 2 times to the t times 2 to the 2 to the t. So here I get plus e, because it has the same, plus 2e, because it has the same base, to the 4t, because I can add the exponents. Notice these two things are now subtracting each other, and all of it is over this squared. This minus that is the same thing, so I can just get rid of them, and I'm left with 2 times e to the 2t over 1 plus e squared. Let's see if I got the right answer. Here, it would be here. Yeah, I did. So the top simplified to that and that. Essentially just follow the quotient rule, find the derivatives of each, and just follow the quotient rule, and it will get you there, and follow the rules of E. The reason I don't like this is, to me, E is just a growth curve. It's just a growth curve that happens to have 2.71, and we should be just studying the growth curves. So here they're looking at very specific derivatives. They want to find you the derivative of 1. Treat the 1/3 as a multiplier, which means you can just focus on taking the derivative of the interior. The derivative of this one is 3 times e to the 3x. That's because you just keep this and then find the derivative of that. And the derivative of this becomes minus 3 e to the minus 3x. Now you might be tempted to resolve this, except we're subtracting, and they don't quite have the same exponent. It'd be tempting to say 3e minus 3e, they get rid of each other. But they don't have the same exponent. That's like saying 5 to the 2 minus 5 to the minus 2 is equal to 0. That's not what that is. That's 1 over 5 squared. So that it's clear that that's not just canceling each other. It's clear it's different numbers. Well, this one here, this part here, is minus 3 over e to the 3x. So it's clear that 3e to the 3x minus this is not 0. Anyway, that is indeed the derivative of that, and it's all multiplied by 3. That's all I need to calculate f of 1. So when 1 here, I get 3e to the 3 minus 3e to the minus 3 times a third. If I resolve that, I get 1/3 times 3e to the 3 minus 3 over e to the minus 3. It depends if they consider that part of the bracket or not. No, it's not. It's a separate thing. So this is definitely what it resolves to. And I'm not sure where they're going to stop, if they want me to then resolve for e, or keep it, oh, this becomes a positive 3 now, or keep it like this. I mean, I could put this on the same fraction by multiplying e to the 3 top and bottom, and I'd be left with e 3e to the 6 minus 3 all over 3e to the 3. It can go on and on and on and on and on. And it depends if they want me to punch e into my calculator and resolve it or not. Let's see how far they want me to go with it. We're talking 4. Oh, it looks like it's even simpler than I came up with. They're claiming the answer is e to the 3 minus e to the 3. I don't buy that's true. Let's go back and do it again. Oh, yeah, I see what's going on. I should have, yeah, actually I did get it. Because when I multiply this 3 through, it's canceling out here, and it's canceling out there. They did forget this part of it. So I'm gonna go back and see again. Just do it again. So you can do them individually. This first part ends up being 3 times e to the 3x. And when it's multiplied by a third, it's clear that cancels out. Oh, I see what they did. And then this other one is clear, ends up being minus 3e to the minus 3x. And it's clear when it's multiplied by a third, that 3 disappears. Then they put in 1 for x, and that's what they got. And I believe that's where they stopped. Yeah. They didn't bring the fraction. They didn't bring this down as the fraction. They just wrote it like that. Fair enough. So we did get it. We just didn't simplify it the way they simplified it. And here we go. We've got e to the power of this, which means the derivative is the same function. But now I've got to take the derivative of this. What is the derivative of that? Well, I'm going to rewrite it as minus 1 times x plus 1 to the negative 1. I've got to use the chain rule, which means this becomes positive 1 when the minus comes down, and this becomes minus 2. And then I've got to take the derivative of the content, which is just 1. Great. Now, I again don't know how much they want to simplify it. But that's it. And keep in mind it's multiplying it. It's not adding it. So there we go. And again, I'm going to just see how far they took it. No, they took it real simple. Okay. Oh yeah, I forgot. I got to calculate for when x is 0. So when it's 0 here, I get 1. So I get 1 over 1. So I get e to the minus 1. And then when it's 0 over here, I get 1 to the minus 2, which is the same as 1 over 2 squared. One to the minus 2 is 1 over, which is 1 over 1 squared, which is just 1. And when I'm multiplying it by 1, I just get e to the negative 1. And that's, yeah. And this time they decide to put it in fractionary form. And instead of saying e to the negative 1, they write it as 1 over e. So all I did was forget to substitute the 0 in there. Let's see if I can do the last one flawlessly or if I'll F that up as well. This time they're talking about z, but it still doesn't matter what they're talking about. Here you have to use the product rule. Have to do z squared times the derivative of the interior, which is just going to be e to the minus z times the derivative of minus z, which is times minus e to the minus z. Then I have to take this function. I have to add it. Product rule. And I have to take the derivative of this, which is 2z, and just multiply it by the function inside. Then I can replace the number with minus 1 in everywhere I see. Wherever I see z. So minus 1 squared becomes 1. So I'll get rid of that. E to the minus z with a negative in front. Well, I should have just kept it as. Should have just kept it as that. I don't think I did the first derivative. Let's try it again so I don't screw it up too. So I'm going to keep this the same, and I'm going to take the derivative of this, which is just this, time, oh, that's where the minus came from, time the derivative of that. So I get minus here. Let's just keep that as minus. Then I'm going to add it to the derivative of z times the content. Okay. So that's just a multiplier. Okay, so when z is minus 1, when h of minus 1, when z is minus 1, I get 1. And I get minus times e to the 1, which is just minus e. When that's minus e is times that 1, I just get minus e. And then 2z here is 2 plus 2 times 1 plus e to the negative 1 again, which is 1 over e. Woof. If I resolve that, it's minus e plus 2 plus 2 over e. Or if I want, to the minus 1. I don't know how far they're going to take it. Let's see. No, they just got a much simpler answer than me. They claim it's minus 2 minus 3e. Don't know if I agree with that. Because we can't subtract these things. They're different exponents. So I'd have to go through it again. And I don't feel like it. I really find some of these mundane. Determine the equation of the tangent line to the curve defined by this. This is the curve at the point 0, 0. The equation of the tangent to the curve. My God. So I've got to find the value of the tangent of the derivative when x is 0. And that will give me the rate of change at that point. Then they want me to graph it. And there's probably some complexities going on that I can't see just yet. Let's try not to screw up this derivative. As you can see, I'm not a big fan. So the derivative of this says I've got to take this, multiply it by the derivative of that. So I'm going to just put it like that, and I'm going to put my derivatives in a box. Then I must subtract this, and it's all going to go into big brackets, times the derivative of this. And I'm going to put that derivative in a box so that I do it. All of it divided by this squared. Phew. Okay, what's the derivative of this? It's simply that. What's the derivative of this? It's simply that. So I'm pretty much left with that. If I expand this, I get that. I can remove the box now. It's clear to me that this will become, when I multiply it, 2 e to the x squared When I distribute this, I get that minus the same thing. Minus 2 to the ex squared, so these cancel out. And I get 2ex minus 2ex. That can't be right. I get 0. Nah, there's no way I got that right. And you can see why I hate these. And I might quit after this one. Usually when I'm this fed up, I just quit because I'm making stupid mistakes. Usually because I don't see the point of it. I mean, I understand this is probably more related to finance than anything. And it's all going to be over this squared. So it's just a question of what my g to the x is. It's this. And it's time my derivative of my f to the x, which is the surface. And that's just the derivative of that is just that. And then I'm subtracting my actual this, and all in big brackets, times the derivative of that. Ah, here we go. There's my mistake. It is just e to the x, like that. There's no 1 in there. Okay, so it's clear to me that this is going to be 2 to e to the x, and this is going to be 2 e to the x cubed, and this is going to be 2 e to the x squared, and this is going to be 2 to the x squared, and these two things are going to cancel out. So I'm going to just be left with 2 e to the x on top. That was my mistake. Like that. Determine the equation of the tangent curve at the point 0. Okay, so that means I have to figure out when x is 0 up here. This becomes e to the 0 becomes 1, so I get 2. E to the 0 here becomes 1. This adds up to 2, but 2 squared is 4, which means the slope there is 2, or half rather. If I'm going to determine the tangent line, I have to take y is equal to mx plus b. It's clear my m is this, and the points they gave me is 0, 1. So I give 1 is equal to half times 0 plus b, and I get my b is 1. So that means my equation for my tangent line is a half x plus 1. Let us see if I even came close. It would be nice if I did. Yeah, I did. There it is right there. A half x plus 1. Now let's use the graphing technology. This is the curve. We're going to pull open a different one. We're going to make it equal to y f of x is equal to, and I'm still going to quit after this one, 2 to the ex divided by 1 plus e to the x. So that's the curve. We're looking for point 0, 1, which is there. We're looking for the derivative of 0, which is 0.5, and therefore we're going to draw the line that we came up with. And half x there. Oh, half x. A half times x. There we go. And when we zoom in, we can sort of see what's going on. And I guess it sort of makes sense. And again, compare the equation part A with the equation generated by graphing technology. Oh, I guess I should have. I guess I should have taken the derivative of that. Let's graph the derivative of that. See if it'll just graph the derivative. get rid of all the other stuff, and we'll just show us the derivative as well. This is essentially showing us that the slope goes up and then slowly goes down and flattens out for this curve. So I'm not sure what they're asking, and I can't see the point of it. Determine the equation of the tangent of the curve and the tangent. Okay. Determine the equation of the tangent of the curve. Pretty much what we did. Oh, that's okay. That's interesting. Okay. Determine the coordinates of all points at which the tangent of the curve is defined by this is horizontal. Is horizontal. Okay, interesting. Ugh. Interesting. Okay. I will get to this, and I can see that 6 through 11 is challenging. 12 to 14 is even more challenging, and 15 to 17 is going to be mind-blowing, especially a hyperbolic function.